In this unit, we're talking about functions, and we can describe functions in basically two ways. And today we're going to talk about the algebra view of functions. Now, a function is a relation where each element of the domain, which we sometimes call an input, is paired with exactly one element of the range, which we call an output. Now, there are special notations or special ways that we write functions in an algebra class, but first I'm going to use these mapping diagrams to explain what examples of functions might look like. Now, in this first example, we have two sets of functions, and these are two functions. And the reason for that is because, again, each element of the domain is paired with one element of the range. So every input has exactly one output. And with these mapping diagrams, the input value is on the left, and we get out the output value on the right. So again, essentially, we're inputting these values, 1, 2, 3, and 4, into some function. There's going to be some function that changes these values, and the number 4 in this case changes to the number 35. The number 3 as an input changes to the number 87, and so on. The function is the operator in between that changes an input to an output. And we would have the same option over here. Although it's a different function, this function again takes every input and maps it to exactly one output. Now, here are some examples of non-functions. So these mapping diagrams are not functions. Can you explain why? Well, the problem in this first example is the input number 8. This input 8, is paired with more than one output. And that's a problem when we're talking about functions. What's wrong with these next two? Can you find the problem? Pause the video and make a guess, and resume playback in a moment to check your work. And so the problems that we see here is that the input number 32 in this example is paired with 4 different outputs, and that's a problem. We can't have more than one output. And then the problem in the second example is that 52 is not paired with any outputs, and that too is another problem. Again, we were told that every element of the domain, every input, is paired with exactly, maybe we should make that one really clear. Every input is paired with exactly one output. Now you might be asking yourself, what's the difference between these two examples here? And hopefully you recognize that in this first example, which was a function, every input was paired with exactly one output. So every input had one arrow coming from it. That's okay. Problem with this guy down here is that this one input had several outputs coming from it, and that is not allowed when we work with functions. And the reason why that's a problem is because when we feed a number, or when we give a number to a function, we should expect exactly one answer to come from that function. There should be no misunderstanding the value that comes out of a function based on a given input value. There should be no question as to the result of each calculation. Now, we can show these calculations and show the function operations using the function notation that we've already seen in this class. We use different letters at times when several functions are used within the same problem, but most common we're going to see the function named f. So this is announced as f of x. We could use g of x or h of x and other letters as well. But for right now, we have a particular example with f of x, and we're being asked to evaluate the following functions and then write our answer as an ordered pair. So let's go ahead and do that. If f of x is equal to 2x minus 9, we should find the following. So with this notation, originally we had the letter x in place of our function notation, and that x has now been changed to a -2. So anywhere that I see an x in the original function, I should change that to a -2. So we have 2 times -2 minus 9. Well, that's equal to -4 minus 9, and f of -2 is equal to -13. So if f of -2, and maybe I'll show that at each line, if f of -2 comes out to be equal to -13, then the ordered pair that comes of that is an x value of -2 and a y value of -13. Why don't you try these next 4 calculations? Find f of -1, f of 0, f of 1, and f of 2. Calculate those results and write your answers as an ordered pair. Resume the playback of the video in just a moment to check your work. And here we have the results for those 4 remaining function calculations. Now, the nice thing about calculating these function results and then placing the answers in an ordered pair is that we could plot these points on a coordinate grid and produce a graph of the function. And on this example of the XY coordinate grid, we have these 5 coordinates now plotted, and you can tell that the function f of x equals 2x minus 9 appears to graph like a perfectly straight line. And that would be correct because this is what we call a linear function. Let's look at another example. In this example, we have a quadratic function, and we should know what this graph would look like. Go ahead and pause the video and find the results of each of these function calculations and plot that result, or plot those results on a coordinate grid. So I'm asking you to plot these resulting coordinates on this grid over here. And again, don't forget that we're going to replace every x with a -2 in this first case. So we're looking for the result -2 squared plus 3 times -2 minus 4. And here we have the calculations completed, and if we were to connect these with a curve, it would probably look something like this. And knowing our end behavior about polynomials, we could probably assume that this graph does continue in this direction, and it will loop upward as well. We'll talk more about the graphs of these functions at a later date. Today we're really just worried about being able to compute the function results based on the algebra. Now, in addition to evaluating single functions, we should be able to combine functions with addition, subtraction, multiplication, and division, as well as some calculations that we call composition of functions. So in this first case here, we are being asked to find what f of -3 is plus g of 7. Now I'm writing it two ways in this video. This is one way to write that calculation, and this is another way to write the same thing. So Whoops, actually it's not the same thing. This example on the right is telling us to evaluate both the function f and g at 7. So actually I do want to ignore that one. And these over here, yeah, all of these are a bit misleading. So go ahead and cross those out on your page. The combination at the bottom is okay, or composition at the bottom is okay. On these two here, I want to evaluate the function f at -3 first, the function g at +7 second, and then add those two together. So the function f a moment ago was 2 times x minus 9. So for this piece of the equation, I'm going to think 2 times -3 minus 9, and this will complete the calculation at f, and then I'm going to complete the calculation g at 7. So this one we're going to add to it, and to evaluate the function g at 7 means to take 7 squared plus 3 times 7 minus 4. And that would take care of the g portion of our calculation. Now again, these functions, the definitions for them came from the equations that we were using just a moment ago, the functions that we were using earlier. And so the function evaluated at -3, f of -3, comes out to be equal to -15. G of 7, the function g evaluated at 7, comes out to be 66. And when we add these two together, we get a result of 51. So f of -3 plus g of 7 is equal to 51. Try the next three problems on your own by first evaluating each function and then applying the operation sign that's in between. Don't forget to cross out or scribble out the second portion of that equation. That's a bit misleading, and we'll talk more about that in class. And here we go with the remaining calculations. We already found f of -3 and g of 7, so I just reused those from the last step. The only difference this time is that we were subtracting in between. So -15 minus 66 is -81. So that's what f of -3 minus g of 7 is equal to. For f of 6 times g of 7, well, I had to recalculate f of 6. That came out to be equal to the number 3. And g of 7, we knew that was 66. Now, 3 times 66 is 198. So f of 6 times g of 7 is equal to 198. Finally, had to recalculate f of 3 and g of 0. F of 3 came out to be equal to -3, because 2 times 3 minus 9 is -3. And g of 0 is equal to 0 squared plus 3 times 0 plus 4. -3 divided by 4, well, that's -0.75 if you used a calculator, or if you left it as a fraction, I'm okay with that answer too. Now, to finish out this video, I do want to talk about what's known as the composition of functions. Composition of functions. And that's where we use a function result as an input to another function. If you think about our order of operations, the order of operations say to do whatever inside the parentheses first. And if we have multiple sets of parentheses, then we go to the innermost parentheses first and work our way out. And in this first example, in this first set of notation, or first example of notation here, we have the function g of 3 written inside the function f. So this tells me that I should evaluate what g of 3 is first, and then whatever that answer is, I will apply to the function f. Now we have another way to note that, or to show that on paper, and that's with this composition symbol. Kind of looks like a multiplication sign when we use the dot for multiplication, but it's an open circle instead of a closed one. So let me show you how I would complete this. Again, I'm looking for g of 3 first. That's the innermost function, so I should calculate what g of 3 is. Now that g function says to take x and square it, plus 3 times x minus 4. Oops, I just realized I made a mistake back here. This should have been a minus 4. With that change, this would have been negative 3 over negative 4, which is the same as 3/4. 3/4, not negative 3/4. This is a better answer to that last problem. Okay, sorry about that sidetrack here. Let's finish out this one. 3 squared is 9. 3 times 3 again is 9, minus 4, so that's 18 minus 4. That looks to be 14. Now 14 is the result of just the g function evaluated at 3. Now that I know what g of 3 is, I'm going to go back into the f function and evaluate that result. So next I'm going to take this and evaluate f at 14. Now that said to take the number 2 times x and subtract 9 from it. So this is 28 minus 9, or in other words, 19. So f of 14 is 19, and this is exactly the same as f of g of 3, also known as the composition of f with g evaluated at 3. Now let's flip those around. Let's complete the g function composed with f at 3. So I'll first start with f of 3. F of 3 is equal to 2 times 3 minus 9, which is 6 minus 9, and this is equal to negative 3. So now I'll work backwards and take this negative 3 and put it inside of the g function now. So negative 3 squared plus 3 times negative 3 minus 4 is equal to 9 minus 9 minus 4, which is equal to negative 4. Even though the function g evaluated at negative 3 is equal to negative 4, that's the same as us saying g of f of 3, or the function g composed with the function f at 3 is also equal to negative 4. And we'll talk more about these in class tomorrow, and feel free to ask me questions about them. We're going to continue to practice this, especially the composition of functions for the last few days of this week, and hopefully this will get you better prepared for our work at the end of the week.